Okay. Okay, so my goal this morning will be threefold, I would say. First, we'll talk about the course outline. So I will just describe the different concepts we'll see together during these 10 or 12 weeks. Then in this set of slides, then I will give you some introduction to artificial intelligence. We'll try to sketch exactly what is meant by these two words. And then in the second part of today's lessons, we'll cover what is known as intelligent agents. Okay, so the outline for this course is as follows. So you will be given 12 lectures in total. 2 of them are being given today, so lecture 0 and lecture 1. Then next week, you will have lecture 2 on solving problems by searching. Then we'll talk about adversarial search, which is the kind of search algorithm that you need when you have multiple agents in the same environment. This year I've decided to remove one of the lectures, which was known as constraint satisfaction problem, which was about going deeper in this kind of algorithms. But I've decided to not cover this material anymore, but still the materials, the lectures and the slides are there on the GitHub page if you want to see them and learn about that. But starting from this year, this material, lecture 2B, will be optional, okay? Then we'll have a series of lectures which will involve uncertainty and probability theory. So this will go from lecture 4 to lecture 7, and we'll talk about representing uncertain knowledge, inference in Bayesian networks, reasoning over time, and then finally we'll introduce some bits of machine learning. And then we'll join all these things together in order to implement rational agents that are able to make decisions under uncertainty. And so this will be the content of lecture 8 and 9 about making decisions, and then a very shallow or first introduction to reinforcement learning. And then finally, you will have 2 last lectures. Lecture 10, which is about communication, which is more like some kind of proof of concept. So like applications of the kind of algorithm we would have seen before apply to communications, like how do you do text translation, how do you do text to speech or speech to text. And you will see that this kind of the kind of algorithm that we would have seen before also apply to these problems. And finally, we will conclude this course, if we have time, with a short lecture on artificial general intelligence and beyond. So schematically, you should picture the way the lectures are organized in this way. So in today's lectures, we'll talk about AI and intelligent agents, and you should consider these lectures as easy. And then we'll have basically two paths in this content. We'll start with the left part of this diagram, in which we'll present and cover search algorithms. So we'll talk about solving problems by searching, and then adversarial search. And also you have the optional lecture to be on constraint satisfaction problems. This is the first part, and I would say the easy part of the course, or what usually students consider as easy. And then we'll take the left part of the right part of this diagram with lecture 4, 5, 6, and 7, in which we'll introduce uncertainty. Okay, so we'll start with a recap on probability theory. So this will be the content of lecture 4. So representing uncertain knowledge. And then we'll have a lecture on inference in Bayesian networks. So Bayesian networks, we'll see, is a way to represent a joint probability distribution, and then inference is basically the problem of making queries on these networks. Okay, and then we'll see how to combine all these tools to be able to reason over time. So given that we act in an environment which is evolving, how can we maintain a belief state which makes sense. Then we'll talk about machine learning, still using this framework of probability theory. This will be the content of lecture 7. And then, so this part, lecture 4 to 7, usually are considered as difficult, even though you already have had classes before on probability theory and statistics. Should not overlook these 4 lectures. Then in lecture 8 and 9, we'll combine these two things together, so search algorithms or planning with probabilistic reasoning. And this is what you do in order to implement agents that are able to make decisions. And finally, we'll see how to combine the last piece, which is how to integrate machine learning in this framework in order to have agents that not only are able to make decisions under uncertainty, but are also able to learn about their environment while doing so. Okay, and then you have these two, I would say, less important lectures, lecture 10 and 11, in green again, about communication and AGI. Okay, so I see there are 2 or 3 questions in the chat, sorry for the delay. So the projects are solo or in groups. You will be able to work in groups up to 2 or 3 students, I don't remember, but yes, you will be able to work in groups. And will the lectures be available at any time on your channel? Yes. So after the live stream, I will edit the video. I will edit the live stream in order to extract videos for each part of today's lecture. A last question. English, no, 2 more questions. English will be mandatory to answer questions at the exam? No. So I know that many of you are still in 3rd bachelor. So during the exam, you can either answer in French or in English, whichever you are more comfortable with. Okay. Do we need to have a strong knowledge of stochastic processes in order to follow the course? I would say no, because we'll see that again, and in particular when we talk about reasoning over time in lecture 6. But of course, if you have already seen that, it's maybe a good idea to go and refresh your mind about what was seen in these previous courses. Okay, so I will just move on. So my mission really in this course, I could summarize this in the following way. So by the end of this course, I hope that you will be able to build autonomous agents or understand how they work, and autonomous agents that efficiently make decisions in fully informed, partially observable, and adversarial settings. So don't worry if you don't understand the words I'm saying, we will describe that today. Your agents will draw inferences in uncertain environments and optimize actions for arbitrary reward structures. Okay, and so really this first paragraph is a good summary of everything we will see during these 10 or 12 lectures. And if you look at what is usually referred as artificial intelligence, you may think that maybe this view is too broad, because usually these days we summarize artificial intelligence as machine learning, but really in this course I want you to understand that artificial intelligence is not limited to machine learning. We'll see, of course, that this plays a very this is a very important component today, but this does not solve all the problems. So the techniques that you will learn in this course will apply to a wide variety of artificial intelligence problems, and really will serve as the foundations for further study in any application area you choose to pursue. Okay, so this is really important. Many of the algorithms that we'll see together, of course, you can use them to implement intelligent agents, but you can apply them to many scientific problems, more classical or traditional problems that you may encounter. So this course, in terms of where is this course with respect to the other courses that you may find in the catalog of courses at university. So I would say that really this course is designed as an introduction to the many other courses that are available to you. So that includes, of course, the introduction to machine learning. So most of these courses, you will be able to follow them during your master, or all of them actually, except for this one today. And usually it goes as follows. You start with introduction to machine learning. Then we have 2 more advanced courses on machine learning. One is about deep learning, which is like a family of methods that are known as neural networks that you have in machine learning, and this course is only dedicated to that. And then advanced machine learning, which is like a course organized as a journal club where we read scientific and discuss scientific papers. So this is a really nice course if maybe you are hesitating and want to for example, you would be considering a career in research, and you want at least to know or to have a gist of how research is done. I think this is a really nice first introduction to that. Then we have a course about optimal decision making for complex problems, which is basically a course about reinforcement learning. Then you have several classes, but courses on robotics, but I've only included one here, which is known as Introduction to Intelligent Robotics. Then you have another one which is called Knowledge Representation, a third one, Computer Vision, and so on. I would also say that this course, Introduction to AI, is related to courses that you may perceive more as like courses on mathematics, and you will see that indeed there is huge overlap between all these fields. So this is why I think you can relate AI to, for example, information encoding theory, to large sample analysis, and others that are not listed here. And finally, you should know that all the methods, the algorithms that we'll see in AI here in this course, or broadly speaking in all of these other courses, have huge social and societal implications, and you should be aware that there is no a legal context which is building around that, and which is covered in a course which is given in the Faculty of Law, and which is known as Introduction to the Law of Robots. Okay. So what time is it? Okay, so I will first try to describe what is artificial intelligence. And so if I just give you these 2 words, some of you may think or may have in their mind this picture, which is a Terminator. And so it's, when you say artificial intelligence to anyone, it really triggers a rich imagination, which is fueled by science fiction, in the literature, or in movies, and in which you think that AI is necessarily like killer robots like Terminator. So this is something which is common, and which is highlighted also by several famous people like Elon Musk, who says that with artificial intelligence we are summoning the demon. So this is an image which I would say is really a caricature of what is AI today, and this is really not the picture that you should have in your mind when we talk about AI. I would say that maybe unfortunately or fortunately, I don't know, that AI today is really closer to this, to a washing machine. And so this is a quote from Fei-Fei Li, which is the director of the Stanford AI Lab. And she says that actually we are really closer to a smart washing machine than Terminator. And I think this is really true, even though maybe it's not that sexy. Today, artificial intelligence agents are really good at performing a few tasks. So this is what we call narrow artificial intelligence, and they usually are able to solve a set of specific tasks in a way which is often superhuman. So you are able to build machines that perform better than humans, but only at some specific task. And you could not use the same agents to solve another task. So this is why we call that narrow artificial intelligence. They are very, they are very good at one task, but not at a large array of other tasks. And this is the same for a washing machine. It's very good at washing your clothes, but you could not ask the same machine to cook your dinner. Okay. So before trying to define the contours of artificial intelligence, I would like first to maybe just take a few slides to reflect on these two words. And for that, I will take this quote. So this is an actual conversation which happened between Dijkstra and Valiant. So the two of them are well-known and famous computer scientists, and I'm quite sure you have seen algorithms from these two guys before. And when Leslie Valiant was a young grad student starting his PhD, his research, he met with Dijkstra, and Dijkstra asked him, "What do you actually work on?" And what he replied, because at the time it was also, there was already a lot of hype about artificial intelligence. He replied that he was working on artificial intelligence. And then, maybe quite genuinely or actually quite deeply, Dijkstra replied, "And why don't you work first on the intelligence part?" And I think this is really true. If we want to build artificial intelligence, maybe we should start defining what is intelligence in the first place before trying to make it artificial. And this is something which is still very elusive. We can barely define what is intelligence, so how can we define what is artificial intelligence? But then if you push this argument further, and this is a quote from Marvin Minsky, who was a computer scientist famous for his work on AI, he said the following. So, but actually when you think about it, what is intelligence anyway? Okay, so it's only a word that people use to name those unknown processes with which our brains solve problems we call hard. But whenever you learn a skill yourself, you are indeed usually less impressed or mystified when other people do the same. And this is why, and this happens today very often. As soon as we are able to, for example, build a computer which is able to beat the best players at the game of chess or the game of Go, then as soon as we are able to do that, you can see people saying, yeah, but this is just an algorithm, and even though, okay, we thought this was a big contribution, it's just an algorithm, and this is really still not really what we want to mean by intelligence. So this is why I think the meaning of intelligence seems so elusive. It describes not some definite thing, but only the momentary horizon of our ignorance about how minds might work. And this is why it's hard for scientists who try to understand intelligence to explain precisely what they do, since our working definitions change from year to year. But this is actually not that unusual for scientists to aim at moving targets. Okay, so I think this is something to keep in mind. First, why focusing on artificial intelligence? Why not intelligence? And then what is intelligence in the first place? And we don't have clear answers for these two things. Maybe a more concrete definition will be the following, which is a short video by Yann Lequin, who is the director of research in AI at Facebook, and which will give you maybe a more modern version of what he thinks is artificial intelligence. So I will just play the video.
Alors, je m'appelle Yann Lequin, je suis directeur scientifique de la recherche en intelligence artificielle pour Facebook. Et je travaille beaucoup sur des techniques qui permettent de faire que les machines puissent, par exemple, comprendre un texte, reconnaître une image, traduire un texte dans une autre langue, sans être directement explicitement programmés, mais en étant entraînés à partir de données. Une grande partie des systèmes de Facebook sont construits autour de l'intelligence artificielle, pour que Facebook puisse décider de montrer des contenus qui sont les plus susceptibles de vous intéresser. Ce que fait l'automatisation et la robotique et tout ça, c'est diminuer la valeur des choses qui peuvent être construites automatiquement, mais augmenter la valeur des choses pour lesquelles il y a une contribution humaine très claire. Donc ce que ça veut dire, c'est que les métiers du futur sont les métiers créatifs. Les gens ont des peurs un petit peu, des fantasmes à cause de l'image de l'intelligence artificielle dans les films d'Hollywood, dans la science-fiction, etc. Les histoires sont toujours beaucoup plus intéressantes quand il y a des catastrophes. Donc bien sûr, on est un petit peu conditionné par ce qu'on voit. En réalité, l'impact de l'intelligence artificielle va être incroyablement bénéfique. Par ailleurs, il y a des dangers de dérive, de mauvaise utilisation de l'IA, etc. Alors il y a bien sûr les scénarios catastrophes à la Terminator où un savant fou découvre le secret de l'intelligence artificielle et puis construit un robot qui immédiatement domine l'humanité. Ce scénario est complètement improbable. Le développement de l'intelligence artificielle ne va pas être un événement. Ça va être une progression, et ça va être une progression qui va impliquer une très large quantité, population de chercheurs et d'ingénieurs, etc. Ce ne sont pas des choses qui peuvent se faire en secret par une seule personne, ça va prendre la communauté entière. D'autre part, il n'y a pas de raison de penser qu'une machine voudra dominer l'humanité simplement parce qu'elle devient intelligente. Il y aura peut-être des machines intelligentes autonomes qui seront aussi intelligentes que les humains dans tout un tas de domaines. Il va falloir enseigner à ces robots à bien se tenir en société, mais comme on le fait avec des bébés humains. Alors tout ça, c'est de la science-fiction pour l'instant, parce qu'en fait, on n'a pas du tout la technologie pour ça, on n'a même pas les concepts scientifiques, en fait, pour permettre à une machine d'être intelligente au niveau de l'intelligence de l'humanité, enfin, de l'intelligence humaine. Pour l'instant, on peut faire des machines dont l'intelligence est très étroite, c'est-à-dire qu'on les entraîne pour une tâche très particulière, et pour cette tâche très particulière, elles peuvent avoir une performance surhumaine. Les machines les plus intelligentes qu'on a à l'heure actuelle sont, d'une certaine manière, moins intelligentes qu'un rat. Combien de temps ça va nous prendre à faire des progrès significatifs dans cette direction? On ne sait pas. Il se peut très bien qu'il y ait un progrès significatif l'année prochaine, ou dans 2 ans, ou dans 5 ans, ou dans 10 ans. Si ça prend plus de 10 ou 15 ans, je pense que les gens qui financent les recherches pour pouvoir faire ça vont commencer à se fatiguer et à ne plus vouloir investir massivement dans ces domaines-là.
Mais pourquoi? Je n'ai pas encore la fibre chez moi.
Bonjour, je m'appelle Jérémy Bonan.
Voici Jérémy.
Okay, so that was it for the video. Okay, but still, I think we need some kind of working definition of artificial intelligence for this course. And so if you go and open the textbook that I was talking about earlier, they actually gave 4 different definitions. And we'll go through each of them, and then we'll pick the one that we will actually make use of during this course. But you could say that there are, broadly speaking, 4 kind of definitions. You would say that artificial intelligence is the science of making machines or programs or stuff that you build that would either think like people, so by that we mean they would try to reproduce exactly the mechanism that we do use as humans to be able to think and reason, or they would just be able to think rationally, even though they may not be built using a machine which mimics how the actual brain works, but still the final result would be that this machine is able to think rationally. Or, and this is the second row for these definitions, you don't really care exactly about thinking. What you want is for the machine or the program to act. And either you want this machine or this program to act like people, or to act in a fashion which is rational. Okay? So we'll go again over these 4 definitions to make things clearer, and then we'll pick one of them. So I will start with that definition, acting like people, so or acting humanly. And basically this is the definition given by what is known the Turing test. And the Turing test is a test in which a computer passes the test if a human operator, after posing some written questions through his computer, cannot tell whether the written responses that he got either came from a person or from another computer. So basically you should imagine that there is someone having a conversation through his computer, but he does not know if he's speaking either to a machine or to another real person. And then the machine at the other end passes the test if that person is not able to tell whether she or he was speaking to a machine or to another person. Okay, so this is a test which was proposed in the 50s by Alan Turing. It's also known as the imitation game. And I think this is still a good test because when you think about it, an agent would not be able to pass this Turing test without the following requirements. So the first one is that the machine should be able to process natural language, because it will communicate with the person through English sentences or French sentences or whatever, which is natural language. So it should have a way to understand what is meant by these words. Of course, it should be able to have some kind of knowledge representation, because, for example, the operator would like to ask questions which will involve some facts or knowledge that we have to represent in some way. Also, this machine should be able to reason, because you could ask questions like, you could describe, for example, a story, you could tell a story to the machine and then ask a question which would involve reasoning. Okay, and the machine should be able to then perform this reasoning task in order to properly answer the questions, as we are all able to do as humans. It should also involve some bits of machine learning, because you could teach new facts to the machine when you discuss with them. And this is exactly what I'm doing today. I'm teaching you new concepts, and hopefully you will all be able to learn part of them. So that means in your brain you have some kind of mechanism that allow you to acquire new knowledge, to learn. Then there are other versions of the Turing test. One of them is called the total Turing test, and which would be like the physical implementation of the Turing test, in which not only you don't want to be able to tell if you're talking to a machine, but you are also trying to impersonate this machine inside a robot. Okay, and so then this would involve computer vision and robotics. Okay. So this is a definition which was proposed 70 years ago, and I still think it's relevant today. There are still no satisfactory solution which passes this test, actually. No machine perfectly passes this test, but there have been many great improvements, great progress in the last few years, actually. And so in this video, what you see is a conversation between someone typing some text and then a machine, a robot, a program, which replies to the questions. So this system is based on a neural network, which is known as GPT-3, the third version of that algorithm. And so you see that all the answers that the program makes make sense. And if I did not tell you that this conversation was between a person and a robot, then I don't think you would have suspected that all the answers were generated by a neural network. Of course, if you are the operator and your goal is to assess whether or not you are talking to a robot, then you would not ask the same kind of questions. You try to probe the weaknesses of the program in order to reveal whether or not that machine is able to reason, that machine is able to acquire knowledge, that machine is able to answer corner questions in which you would be trying to trick it. And so this is why this test actually has many limitations when you think about it, because you would then tend to focus on human-like errors, on linguistic tricks and other things, and not really on artificial intelligence itself. Okay, so this is why I think it seems more important to study the principle underlying intelligence than really to try to replicate one of them. So to give you an analogy, if you look at, for example, the field of aeronautic, aeronautics is not defined as the field of making machines that would fly so exactly like pigeons that they can fool other pigeons. Okay, and this is exactly the same for AI. We should not, I believe, define artificial intelligence as the field of making machines that would speak so exactly like us so that they are able to fool us. Okay, and so I think this is really important, and it's more important to study the underlying principles that would at the basis of intelligence in order to try to develop artificial intelligence. It's the same for aeronautics. We've not, I mean, we started with this kind of prototypes where we try to replicate exactly the wings of birds, but this didn't work at all. And then we had to depart from this analogy and really to study for example, the aerodynamics of the machine in order to be able to make it fly. Okay, and I think this is the same story for AI. Okay, so let's now go to a second definition, which is the one of thinking in human fashion. And by that I mean trying to reproduce exactly the mechanisms that we implement in our brain in order to have reasoning or thinking. So with this definition, there are actually two approaches. I would say that there is one which you could view like a top-down approach or top-down definition, and the other one is the opposite. It's a bottom-up approach. So the top-down would be exactly what is the objective of cognitive science. So cognitive science is the study of the human mind and all the processes of the human mind. And really the goal of cognitive sciences, which by the way is a field which emerged from good old psychology, is to form a theory about the structure of the mind. And you would like to have these theories to be as so precise that you can actually write a computer model, implement a computer model of this theory. Okay, and so this model would include, of course, language, problem solving, decision making, and perception. And usually, this computer model is described as what is known as a cognitive architecture, which will usually follow human-like reasoning and can be used to produce testable predictions, like the time of delay during problem solving, kind of mistakes, learning rates, and these kind of things. And so this is one of the most modern cognitive architecture, which is known as SOAR, in which you see that you have different boxes that are very high level in a sense. You just try to describe in a logical fashion how these components would act together. And so you see that at the middle you have you have a working memory, and then at the top you have long-term memory, which is itself divided into other compartments. And then there are different kind of interactions between all of them. Of course, this mind lives in a body, and this body is able to through this body you're able to perceive your environments through your eyes, what you hear, and so on, what you touch, and you can also take action through this body. Okay. So this is a top-down approach because you start really with the abstract concept of memory, perception, and so on, and you don't start with how these things work, for example, at the cellular level. Okay. If you do this approach, so instead a bottom-up approach, then basically this is the study of neurobiology and neuroscience, which is more about the anatomy and the physiology of how the brain works. So by that I mean at the cellular level, and how aggregates of these cells together form something which implements the brain. Okay. So neurobiology by itself is concerned with the anatomy and physiology of the brain, from major structures down to neurons and also molecules interacting with these neurons. Okay. And then, so this is just about the anatomy, and then if you take a step back, then you have neuroscience, which adds to that the study of how the brain works as a whole, mechanistically, functionally, and systematically to produce a behavior that you observe. Okay? But So both of these approaches, cognitive science and neuroscience, I would say, have the same goal. You want to understand how we are able to think as humans. Okay, they just take two different paths, but their goal is the same. Okay. Again, I would say that there are limitations to these two approaches. With regards to AI, of course, they are very interesting from a pure scientific point of view, because it's really, I believe it's really important to be able to understand how we think as humans, but it may not be that important when it comes to implementing AI. Okay. And anyway, one of the strongest limitations was raised by Noam Chomsky in the 80s, and he came with the following questions. So he did a lot of study in linguistics, in cognitive science, and in particular with respect to child development. And he came with the following questions, which was, how do we know what we know? And basically he realized that if you look at small child, within 1 or 2 years, they are able to speak and to understand almost everything that you are telling them. Okay? But if you just barely count how many sentences they would hear within this window of time, then he says that there are just too few of them to be able to grasp to grasp language. Okay? What he says is that it's known as the poverty of the stimulus. So you don't stimulate enough the child such that it could learn that from scratch. So he says that children do not receive sufficient input to generalize grammatical rules through linguistic input alone. Okay, and what is important is the alone. And so his hypothesis is to say, so if the input is insufficient, that means that child, and this is an hypothesis, come with something when they are born. Okay, so by that he means that humans must be in some way biologically pre-wired with some kind of innate knowledge. So you are born with some innate knowledge from the start, and this is this innate knowledge that then enables you to quickly grasp language. Okay. So that means now, if we are still considering this approach of trying to reproduce exactly the human brain, be it from the cognitive science point of view or the neuroscience point of view, that means if this hypothesis is true, that will only be possible if we are able to inject this background knowledge of some sort in order to initialize the model. And so this is a really huge obstacle, because that would mean we would be able to reverse engineer the brain, and in particular the brain as we have when we are born. So this is a huge obstacle by itself. Not that it cannot be done, but this is a huge obstacle if your goal is to implement AI in this way. Then the third definition is that I would go over is the one of thinking rationally. And so this is known as the logical approach to AI. So rational thinking, so this is something which has been studied for centuries, even not more, in philosophy. So rational thinking is concerned with the study of irrefutable reasoning process, and such that this reasoning process will ensure that all actions that would be performed by a computer are formally provable from inputs and prior knowledge. And so this is a trend in AI which was very popular from the 60s to the 90s. It's no longer the case today. I could even say this approach has really died out. But I think it's still interesting to know that this exists. And basically their goal in the laws of thought, these laws were supposed to govern the operation of the mind. And this is what really initiated the field of logic and the logicist traditions of AI. So even though this is not how we are doing AI today, it contributed to, I think, many important discoveries and tools that you can use today to solve computer science problems or other problems. And so, for example, you can use this kind of tools to, and I think this is quite interesting to know as computer scientists, with this kind of framework, you are able to write computer programs in which you don't write computers to solve the problem, but what you only do as a user is to write a computer program which describes the problem itself. And then you let in this case, for example, the interpreter to take this problem as input, and then the interpreter would solve it for you. Okay, and so this is something which can be done by just taking a few equations from logic, and you initialize this with some prior knowledge, and then you can do inference, logical inference with that. So for example, this is a quiz which is known as the zebra puzzle, which is famous because we say this was suggested by Einstein to assess whether or not you are intelligent. And so this is a quiz where you have a few facts. So there are 5 houses. The Englishman lives in the red houses. The Swede has a dog. The Dane drinks tea. The greenhouse is immediately to the left, and so on. So you have this description of facts, okay? And then the question is quite simple. It's this one: who owns the zebra? Okay, and you should be able to do that on paper. If you are able to do that within minutes, then I would say you are not that stupid. If you are not, don't be afraid. That's fine. But you should be able to put all the pieces together in order to infer who is the owner of the zebra. Okay. If you were to do what I just told you could do, what you can do is to write a computer program that just describes this problem. And so this is something you can do, for example, in language like Prolog. And so this is one of the questions I've seen in the chat, where, okay, you have to know the language, but this is what you see is just the definition of the problem in which you encode all the facts that you have in the sentences. And then what you see, for example, there is you ask the question, who is the owner of the zebra? And then the program just takes everything as input, and then is able to infer that the composition of the houses, their colors, the nationality of the habitant, whether or not the animals, what is drinking, and the kind of cigarette is smoking, are such. I mean, if these are the facts, this is the solutions which satisfies all these facts, and therefore, given this solution, I know that the owner of the zebra is the German. And this is what the program answers. So this is nice, and I think this can broadly apply to a large palette of problems. But when you have to really use that in practice, maybe for more real-world problems, you quickly come into obstacles. And the first one is the fact that representing informal knowledge is difficult. So if there are things for which you don't exactly know how to describe, or things for which you are uncertain, then it's make it very difficult to write these things as for example, Prolog programs. And so this is why then it's very hard to define provable, plausible reasoning. So as soon as you have uncertainty, it becomes very difficult to use, because you could still in some way try to discretize your problem with respect to your level of confidence, but then that would quickly lead to a combinatorial explosion, and therefore just solving for these programs would no longer be tractable in space and time. Okay. And then finally, I would also say that, and this is the most important argument, I would say, thinking rationally is only one part of intelligence. It does not cover everything. Okay. So for example, in many cases, you may be in situations where there is no probably correct things to do. Okay, but still you have to make a decision and do something. Okay. Yes. Then, and another example are reflex actions, in which what you do is that you don't think when you have a reflex action, you just take an action, and these reflex actions can be more successful than carefully thought and reason actions that you would then get from logical inference. For example, if you put your finger on some candle, then you don't even think about it, you remove it. But if you let it there on the candle and then take the time to understand what would be the implications if your finger stayed there on the candle, then the consequences would be worse than just executing this reflex action. Okay? And so this is important because in reality, the time that you have to make a decision, usually you have a limited budget to make this decision, and therefore you know that you will have to be approximate. You will not be able to achieve optimality in all situations because of this limited computation budget that you have. Okay, so we've gone over 3 definitions. There is only one of them, and you can already guess, I suppose, this is the one we'll use for this course, which is the one of acting rationally. And so we say that a rational agent acts so as to achieve the best expected outcome. Okay, and so correct logical inference, of course, would also achieve that, but this is only one way that we could use to implement this rational behavior. Okay, and we'll see that there are other ways to achieve that. Okay, and as I was saying, perfect rationality cannot be achieved usually because you have computational limitations. The budget that you have to make a decision is limited. Okay, so that means the amount of reasoning that you should put when you make a decision should be adjusted according to the available resources that you have, and of course to the importance of the result of your action. Okay, it's like, I don't know, if you were to buy a house, usually this is a decision that takes time to make because you really want to be sure that everything is done properly and that you are making a good decision. And so this is something that you will invest time, you will invest resources because the importance of the result is significant. But I don't know, if you go at lunch at the cafeteria, you will pick a sandwich and you will not think for days to make this decision because the importance of the result is less than the one of buying a house. Okay? And the brain, when you look at it, it is good, it's a good implementation, a good agent in a way to make rational decisions, but again, it's not perfect either. Okay? So we should understand that as humans, okay, we are intelligent beings, but and we can make rational decisions to some extent, but we are not optimal either. There might be other mechanisms that would allow us to make more rational decisions or more optimal decisions. And one thing I would like to insist on is that rationality only concerns what decisions are made, okay, but not the process which is behind it. Okay, and by that I mean we will not really care if this process is implemented through a program that exactly replicates the brain, or if this process is implemented by logical inference. What we just care about is what are the output decisions. Okay, and this is what concerns rationality. And then the goals will be expressed in terms of the performance or utility of the outcome. Okay, and by that we'll say that we'll be rational when we will try to maximize this expected performance or this expected utility. Okay, and this is nice because you will see that we can formalize rationality in very generally and very formally in mathematical terms. Okay. So in this course, the first thing that you should remember is that for me, from now on, artificial intelligence, the working definition that we'll use will be the one in which your agent try to maximize some kind of expected performance. Okay. So what? Yeah. Okay. So now I will go over a bit of history of AI and some more motivation, some actual examples of things that we can do today. and this should last for, I think, another 30 minutes, then we'll have a break. So the first thing I want to say is that the field of artificial intelligence, even though it's new, its roots come from many different fields of many different disciplines. But I think one of the oldest one would be the field of philosophy itself, in which things like logic, methods of reasoning, mind as a physical system, the foundations of learning, language, rationality, all these concepts have been studied in philosophy for centuries. Then, of course, another field which was very important for the emergence of AI is the field of mathematics and many of its subdomains. So, for example, the formal representation and proof, algorithms, computation, decidability or undecidability, interactability, probability. All these things are really important when it comes to AI. And you will see that in particular, probability theory play a very important role in modern artificial intelligence. And without that, you can barely do, you cannot do anything today. Then, of course, psychology, so adaptation, perception, motor control, psychophysics, all these discoveries have like fueled part of AI. Economics also, you can relate AI to economics because in a sense, or part of economics is about having a formal theory of rational agents and their decisions. And this is exactly the kind of things we have just been talking about. Linguistic is another important contributor with knowledge representation, grammar, kind of things. Neuroscience, of course, and I would also mention control theory, in which you have usually some kind of system with a loop, and then you want to control it in some fashion. This is also the kind of things we'll see during these lectures. We'll have a system or two systems, like an agent and an environment. Then you want to take actions, and you will have some feedback from the environment. So all these things are really important concepts when it comes to AI. Okay, so this was really for the prehistory of AI, I would say. But when it really comes to AI, the earliest mentions or things that are really the most closely related to AI dates from the 40s and the 50s. And I would just mention two important contributions. The first one is in 43, the first Boolean circuit implementation of a biological neuron. Then in the 50s, of course, there is this famous paper by Alan Turing, Computing Machinery and Intelligence, in which, among other things, he proposed this Turing test. Then from the 50s to the 70s, there was a lot of excitement and expectations from AI. So in the 50s already, you could see the very first AI programs, for example, to play the game of checkers. Another important contribution is the logic theorists, which implement early prototypes of this Prolog language I was mentioning earlier, and also this geometry engine in which you could ask geometry problems to the machine and it would answer. In 56, there is this important event which is known as the Dartmouth meeting, in which in particular the term artificial intelligence was introduced and then adopted. Then in 58, you have the invention of the perceptron, which is like one of the very first, or I would say it's even, you could say it's the ancestor of modern neural networks. So this is also an important event. Then you have other contributions, and you see that they were involving this logistics tradition by Robinson, for example, and also other important work involving computational complexity. So I was mentioning this Dartmouth workshop, and I think it's quite important, or interesting to see or to perceive how they were conceiving artificial intelligence at the time. And I think it's still quite close to everything that I've been describing. And so in this workshop, which they organized like a 1 week or several week gathering of scientists, the motivation, the abstract said that the study will be about the study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. Okay, and so this is a question that we still cannot answer today, even if we have made huge progress. There are still many open questions, and we are not able to understand everything or how humans were able to learn the thing we learn. So I will just pass now a second video which show you it's a short documentary about this period from the 50s to the 70s, and you will see that already at the time there was a lot of buzz behind this term that we call artificial intelligence.
The thinking machine.
Hello again. With me tonight is Professor Jerome B. Wiesner, Director of the Research Laboratory of Electronics at MIT. Dr. Wiesner, what really worries me today is what's going to happen to us if machines can think. And what interests me specifically is, can they?
Well, that's a very hard question to answer. If you'd asked me that question just a few years ago, I'd have said it was very far-fetched. And today I just have to admit I don't really know. I suspect if you come back in 4 or 5 years, I'll say, sure, they really do think.
Well, if you're confused, Doctor, how do you think I feel?
We're just really beginning to understand the capabilities of the computers.
I've got some film to illustrate this point, which I think will amaze you.
That man isn't playing checkers against a computer, is he?
Sure, and it plays pretty well.
Now, which color?
While most computer scientists saw it as a mere number cruncher, a small group thought that the digital computer had a much grander destiny. Being a general-purpose machine, it could be programmed to do things which in humans require intelligence, play games like checkers and chess, and solve brain teasers.
Let's see what it's turning out.
The field became known as artificial intelligence.
Can machines really think? Even the scientists argue that one.
I'm convinced that machines can and will think. I don't mean that machines will behave like men. I don't think for a very long time we're going to have a difficult problem distinguishing a man from a robot. And I don't think my daughter will ever marry a computer. But I think that computers will be doing the things that men do when we say they're thinking. I'm convinced that machines can and will think in our lifetime.
I confidently expect that within a matter of 10 or 15 years, something will emerge from the laboratories which is not too far from the robot of science fiction fame.
They hadn't reckoned with ambiguity when they set out to use computers to translate languages.
A $500,000 supercalculator, most versatile electronic brain known, translates Russian into English. Instead of mathematical wizardry, a sentence in Russian is to be fed in...
One of the first non-numerical applications of computers, it was hyped as the solution to the Cold War obsession of keeping tabs on what the Russians were doing. Claims were made that the computer would replace most human translators.
At present, of course, you're just in the experimental stage. When you go in for full-scale production, what will the capacity be?
We should be able to do about, with a modern commercial computer, about 1 to 2 million words an hour. And this will be quite an adequate speed to cope with the whole output of the Soviet Union in just a few hours computer time a week.
When do you hope to be able to achieve this speed?
If our experiments go well, then perhaps within 5 years or so.
And finally, Mr. McDaniel, does this mean the end of human translators?
I would say yes for translators of scientific and technical material, but as regards poetry and novels, no, I don't think we'll ever replace the translators of that type of material.
Mr. McDaniel, thank you very much.
Okay, so you can see that already in the 60s there was the same kind of excitement and expectation that you can still see today, and that in particular you can still today, I mean, that we have been having from the last 5 years or so. And for example, the fact that some kind of intelligent robot would emerge from a lab, as Shannon was saying, this thing did not happen yet. The fact that we would replace completely translators, human translators, it did not happen until very soon, and I still think you need them when it comes really to understand the precise liming of, let's say, when you want to translate a book, or when you want to translate poems. We are not able to do that today very well. Even though when it comes to just translating news or Facebook posts or whatever, all of these translations now are made automatically by a neural network, and it works reasonably well. But when it comes to the details, we are not there yet. Okay, then if we move on a bit closer to the present, so between the 70s and the 90s, this was really the era of what is known as the knowledge-based approaches, like expert systems, which were based on this, or was a continuation of this logicist tradition of AI. And in particular, in 1969, Minsky and Papert published a book in which they proved some impossibility results for some version of a neural network. And because of this, most of the research about neural network almost disappeared. I'm saying that because now everything which is driven by AI is implemented with neural networks. So when you look at this story, they almost disappeared, but eventually they came back, and they came back very strong. Okay, so then in the 70s, you have the early development of knowledge-based system, as I was saying, and this really generated a lot of expectation from the industry in particular, but eventually this system basically did not manage to reach their expectations, and the whole field of AI basically burst this time, and this is what is known as one of the first AI winter, so at the end of the 80s. Still, research kept going on. There were a few scientists that were still interested with these ideas, and so at the end of the 80s, beginning of the 90s, some people started working again on neural networks. So a few of them are Yann Lequin, that you saw in speaking in French in one of the previous videos, or Geoffrey Hinton, Yoshua Benjo, and others. So what is important is that it's at this time that really the field started to gain in technical depth. So it's really at this time that people started considering probability theory as a tool to build better agents, to focus on uncertainty and other things. Unfortunately, this return of neural networks quickly faded. So from 95 to 2010, almost no one was working on neural networks because there were other tools that were more fashionable at the time for machine learning. But again, this tool eventually showed their limitations, and this limitation have been overcome by neural networks eventually. What is also interesting from this period is that if you look at, for example, around 95, it was really the first time that we had complete intelligent agents and learning systems. In around 2000, it's also the time where we started having larger and larger data sets. So you will quickly realize that in order, for example, for these agents to be able to learn and to self-improve, you need to feed them with something. And this something is data, and usually the more data that you feed to these learning systems, the better they become. And so if you only have small data sets, then what you can do is limited, but if you can provide larger and larger data set, then of course the performance usually increases. And because of the rise of the internet around 2000, this larger data set became more common. So in 2010, it's also around this time that very fast community hardware became available. So the fact that, I mean, at least regarding neural networks, you need a very efficient and performant machine to run them, and GPUs are a solution to this problem. Okay, and finally, around 2012, really it is the time where you could say that we had a resurgence of neural networks with what is now known as deep learning. Okay, and this deep learning thing is the focus of an entire course, as I was telling, that you can take during your master degree. Okay, so this is about it for the history. I will not go beyond that. What I would like to do now before the break is to go over this list of things, and basically what I'm asking is, what do you think artificial intelligence are able to do today? Okay, and so please you just use the chat to answer these questions, to have some kind of interaction. So do you think today some kind of program is able to translate spoken Chinese to spoken English and is able to do that live? Okay, so yeah, so a few sorry, there is like a 30 seconds delay. I will try to reduce that to have better interactions, but most of you answered yes. And indeed, this is something now which is very common. You can talk to your smartphone in French, and this thing can be translated, for example, using Google Translate, live in English. And this is something we've been able to do quite well for some years now. Do you think now an AI is able to answer multiple choice questions as good as an 8th grader? So like a child from primary school. So do you think it can answer as well as a small kid? So I see 1 yes, 1 no, 1 yes, 3 yes, 4 yes, 5, 6, probably yes. So it's mostly yes, but there are a few no's. That's interesting. So actually this is still quite an open problem. We have now reasonable solutions, and one of you mentioned GPT-3, and indeed you could use this kind of system to have decent performance, but it's still difficult to reach performance which would be as high as a human. And the reason is that in order, for example, to answer multiple choice questions, you really have to have some kind of built-in reasoning. For example, if you read a text and then we ask questions about this text, you need to be able to present knowledge, and then of course you need to be able to understand language. And doing all these things together is still very tricky, even if indeed we had very recent and significant progress very recently. So I will converse with a person for an hour, more or less, but depends what you define as a conversation, of course. Play decently at chess, Go, poker, and soccer. What do you think? Do you think we are able to build agents that are able to play all these games? So there are There is a yes, but not soccer. Go and chess, sure, but not soccer. Okay, yes, except soccer. Okay, there is one interesting answer. Chess and Go, yes. Poker is different because there is a lack of information. Not poker. There is a few not poker. Okay, that's interesting. So indeed, chess and Go. For chess, we are able to do that since the 90s with Big Blue. Go, we've been able to beat the best human player since now 5 or 6 years already. Poker. So poker, it's interesting because in poker you don't have the. So what we say is that you don't fully observe the environment, meaning that there is some information that you don't have access to because you don't know the cards of your opponents and you don't know exactly the cards that are in the stack. And this has been an obstacle for very long, but now since 1 or 2 years, the best poker players are AI programs. Okay, and you can beat, and they play in tournaments and they beat the champions. But this is, again, very recent. The first time I gave this course, like 4 years ago, poker was still an open problem, and I would say this is not possible, but today in 2020, it's possible. And soccer, as you said, and I will show you a video, we can barely play soccer with robots. It's just ridiculous. Do you think we can use AI to prove mathematical theorems? So proving mathematical theorems, usually that's quite difficult for us as humans. What do you think an AI could do that? No. Yes. A few yeses, 2 no's, 3 no's, 4 no's. It's controversial. Some. Yeah. Yeah, okay. There is one answer which says, not sure they classify as AI. So again, you can actually prove theorems, but not all of them. And this is actually some of the outcome of this logicist tradition of AI, in which, for example, one of the things which has been really developed is to have like automated prover, and you just just start with a few axioms and some facts, and then you can then deduce many other things, other theorems from this. But of course, so you can use these tools to prove the few things, but of course, mathematics is not solved, and there are still many open questions. So this is a bit controversial. Do you think we can drive a car safely first on a parking lot and then in New York, or let's say in the city center of Liège? So there is this comment, we can only use this prover or only the one we are able to prove ourselves. So there are many, just to comment on that, there are a few proofs that would not have been, that we wouldn't have been able to have without the help of computers. Yes. So with respect to driving, so I only see yeses. Yeah, so technically I think we are almost ready to go there. And I will show you videos of Teslas and autopilot where you can go from one place to another without even touching sorry, I don't remember the word, but you understand what I mean. Do you think an AI would be able to write a funny story, or to paint like Van Gogh, or to compose music? So writing funny stories, paintings, composing musics. Okay, so that's surprising. You are all telling me yes, which is quite interesting. Not an original one. So let's talk about paintings. So indeed, you have now systems that are able to produce things that would look like paintings, but let me rephrase then the question. Do you think an AI would be able to produce a masterpiece? An original masterpiece? Okay, so now you are all telling me no. That's interesting. You've changed your mind. Okay, and I think, yeah, it's difficult to describe very formally, but we all feel that something is missing. So one of the comments was talking about soul or creativity, and I think this is very difficult to describe formally. And yeah, I would say still, I mean, I'm not sure we'll be ever able to do that, but who knows. And finally, yeah, it's subjective. And of course it depends on the public, on the audience. Okay, and then final question, do you think an AI is able of common sense? Which is something we are all able to do as humans. We don't know how we have this common sense, but we do have it. No, no, no. No. So indeed, having common sense in AI systems, there is one, yes. I would have liked to know more about this one. Okay, but yeah, that of course depends on your definition of common sense, but we'll talk about that much later. But broadly speaking, this is something we barely know how to define in the first place, even less to implement in a machine. Okay. So I will just now go over a few videos again, and many of which are answers to these questions we just answered together. So of course, speech recognition, this is something we've been able to do for almost 10 years now.
I want to come back.
And so for example, there what you will see is one of the first prototypes in 2012.
One of the most natural interfaces
of spoken English translated, I mean, first translate text from speech to text, and then this text, English text to Chinese text, and then this Chinese text synthesized to Chinese speak. And what is interesting then in the system is that the Chinese speech conserve the accent and the tone and the rhythm of the original English speaker.
For people,
and it's not like a robot.
It comes out of Microsoft research. Bing translates millions. Okay. We're basically taking the English text and pushing it through the translation system. We then have to reorder that text in Chinese because the word order in Chinese. So now we're taking the things that I'm saying and we're converting them into Chinese text. Now, the last step that I want to be able to take in this process is to actually speak to you in Chinese. Now, the key thing there is we've been able to take a large amount of information from many Chinese speakers and produce a text-to-speech system that takes Chinese text and converts it into Chinese language. And then we've taken an hour or so of my own voice, and we've used that to modulate the standard text-to-speech system so that it would sound like me. So what you see now is the result of that change. I'm speaking in English, and hopefully you'll hear me speak in Chinese in my own voice. Again, the results are not perfect. There are in fact quite a few errors.
结果并不完美。他们集体反复反错误。
There's much work to be done in this area.
在这方面有很多工作要做。
So you all told me that we could do that, and indeed we can, but what you should remember is that we have been only able to do that for 8 years, and this was just coming out of the lab, and it's been in your smartphone just since a few years from now. So this is just again to show you that this field, artificial intelligence, is still very recent but quickly developing as well. And so how this system in particular works, this is something we'll cover in lecture 10. So you can translate from English to Chinese, but translation is not really having a real conversation. And so, but one of the questions was, can you have like a 1 hour long conversation with a program today? A 1 hour long conversation, I don't know, but at least very short communications, very short exchanges. This is something we are able to do. And so this is, I think, a very impressive demonstration of what we can do today or already 2 years ago. So this is something done by Google with their Google Assistant. And what you will hear, maybe you have seen this video before, is the program taking an appointment on the phone to an hair salon, and the people, the hairdresser, she does not know she is talking to a program. Okay.
As I said earlier, our vision for our assistant is to help you. So let's go back to this example. Let's say you want to ask Google to make you a haircut appointment on Tuesday between 10 and noon. What happens is the Google Assistant makes the call seamlessly in the background for you. So what you're going to hear is the Google Assistant actually calling a real salon to schedule the appointment for you. Let's listen.
So how can I help you?
Hi, I'm calling to book a woman's haircut for a client. I'm looking for something on May 3rd.
Sure, give me 1 second.
Mm-hmm.
Sure, what time are you looking for around?
At 12 p.m.
We do not have a 12 p.m. available. The closest we have to that is a 1:15.
Do you have anything between 10 a.m. and 12 p.m.?
Depending on what service she would like. What service is she looking for?
Just a woman's haircut for now.
Okay, we have a 10 o'clock.
10 a.m. is fine.
Okay, what's her first name?
The first name is Lisa.
Okay, perfect. So I will see Lisa at 10 o'clock on May 3rd.
Okay, great. Thanks.
Great. Have a great day. Bye.
So as you see, this is something we can do today. I don't know if we should say it's a dream or a nightmare, or you pick. But this is a technology which is ready, and also, I mean, as long as you remain within the realm of taking an appointment, I think this kind of service are ready to be released. Of course, if you were to, if the the hairdresser was talking about really something else outside of taking the appointment itself. I'm not sure how the system would have replied, but if you stay within the scope, I think this works quite well. And I'm convinced she didn't know she was talking to a program. Okay, so this was for like speech and this kind of things. I would like now to just go over a few more videos. One of them is about reinforcement learning. So reinforcement learning is something we'll see in lecture 9. And it's a way for an agent to be able to act in an environment. And one of the benchmarks we often use in research is to be able to have agents that learn to play video games. And the only thing that we tell them is you have this set of actions that you can use. This is some reward, like the score of the game. Figure everything else, okay? So the program has to figure out basically that this array of pixels correspond to the screen of a game, and it should be able also to learn what are the consequences of the actions that it takes with respect to the dynamic of the game, but also, and most importantly, with respect to how the reward then will evolve, because you would like to maximize it. And so with standard now reinforcement learning algorithm, you can have this agent to, by themselves, they learn how to play this kind of Atari games. So this one is Breakout. And after a few hours of training, you have good agents that play almost as well as humans. But what is interesting is that, and this is what is shown now in the video, if you let the agent learn longer, then it starts, in some cases, it starts learning strategies. And one good strategy for this game is to dig some tunnel at one of the sides, such that it can trap the ball in this tunnel. And in this way, it will get very quickly a large reward without taking any risk. And this is something, again, which is never explicitly programmed in the algorithm, but which is discovered through learning. The game of Go, this is something I mentioned, so you can watch this video if you want to know more details, but this has been a real challenge because of the size of the state space of the game state space. Because you have a large configuration of 19 by 19, this is the size of the board, and at every move you can pick basically a position about this 19 by 19 cells, and so this grows very quickly if you were to consider all possible configuration of the games in order to decide an action. This is something you cannot do because the space is just too large. You can also now use AI programs also to play real-time strategy games like StarCraft 2 or Dota 2, and they become stronger and stronger these days. And so you can watch the video. Again, this is from 2 years ago. You can find on YouTube other videos, in particular from StarCraft 2, and they are among the strongest players for these games. And this is interesting there. I don't know if you know about that, but because you have a very, you don't know everything, so the environment is only partially observable. You don't have access to the full information about the game. And you have to take many actions per minute. It's not one action and then you wait for 2 minutes for the player to do something else. You have to take actions at all time steps, basically. So it can range from 60 to a couple of hundred actions per minute. And then you have many units that you have to control, you have an economy to manage, and so on, and all of these things together in order to beat your opponent. So this is a very complicated game by itself, but again, now we have AI systems that are able to beat the best human players. We mentioned soccer, and indeed this is something we can barely do today, even though on all these other video games we are able to play very well and better than humans. On soccer, we cannot play very well. So this is what you see is the final of the 2018 RoboCup. So these are the two best teams, and they play against each other.
Nice.
Yeah, so you can see there is still a lot of work to do. It's very silly and ridiculous, and this is state of the art. And the reason is that when you have to act in the real world, then you have so many things that you have to plan for that it becomes very, very, yeah. So one comment is that white is clearly better than Mbappe, and yeah. Anyway, so this is just to say there is still a lot of room for improvement, and we still need young minds to help. So engineers like you and computer scientists like you, we have not solved all the problems. And in particular, when it comes to the real world, so systems that have to interact with reality, you have so many unknowns that you have to anticipate that everything becomes so difficult. Okay, there is this one. Most of this example has been. Okay, so there is one thing I will answer on the chat. You can use the same kind of algorithm to also not play video games, but to learn how to control machines, or in this case, this kind of little characters, and they would learn how to do it by themselves. I can just play the video. And so again, what is interesting in the systems is that the only thing you program, so that you give to your AI program, is what are the actions that you can take. This is some environment you will live in, and this is the reward that I want you to maximize. And then the program has to figure out basically a strategy to maximize this reward by executing a proper sequence of actions that would maximize this reward. So in this case, the reward is to go as far as possible in this world by controlling all the joints of these little characters. So they have to learn to walk or to run or to jump by themselves. Okay, so let's move on. Then there was this question about driving a car, and I will come back to the question in the chat just a bit later. So can an agent drive a car? So I would say technically yes. So this is a video from 4 or 5 years ago by NVIDIA, and you see that already 5 years ago, which is not too long ago, we had this kind of system that managed to drive the car. And again, what is interesting is that it's the same kind of it's the same kind of algorithm, the same kind of methods that is used in this system than the ones to play video games, for example. You have some kind of learning system that has to interact with the world, with reality, and then has to make sense of everything it does and observes in order to learn a policy for driving properly, in this case. Of course, this looks easy like this, but this is really like a feat of engineering, because this car is like covered with different types of sensors, many cameras, built-in cameras that register everything around the car. And then for this to work, what you have to imagine is that then the car has to make sense of the environment around itself. So this is itself quite difficult. Then it also has to figure out or to learn the dynamics of the maybe object that would be moving around itself, like other cars. And then of course it has to learn to stay on the road and not to walk on pedestrians. And you cannot afford having mistakes or many mistakes at learning time. So this also give rise to many obstacles when it comes to training. You could not let a car let itself learn how to drive by just, give it freedom and put it on the highway. Would just make accident and destruct the car immediately. So usually what we do when we try to develop the system is first we learn everything in simulation in control environment, and then we deploy the learn policy in the real system. Of course, then you have some other issues, like there is a gap between simulation and reality. How do you cope with that? How do you make it robust? Or how do you anticipate things that may happen in reality but would not happen in your simulator? All these things are open questions. So of course you can use that to learn, of course, to not drive your car anymore, and this comes with many concrete applications. One of them is to prevent accidents. So for example, in all Teslas today you have autopilot, which may or not be activated, enabled everywhere in Europe, I don't know, but in the States this is something that you can use. And this is, I think, a very nice and concrete application of today's AI, is that the program autopilot is able not only to drive the car, but if you want to drive the car yourself, the agent autopilot can take over in case it anticipates an accident. And this is something that you see in this video. For example, the maneuver of the car going to the right is something which was not done by the driver, but which was done by the program. And again, to be able to do that, that means you have to understand the dynamics, you have to have a good knowledge of your surrounding environment, and you also have to be able to anticipate the future, because the system has to say, okay, I think 3 or 5 seconds from now there will be an accident if I keep driving the way I'm driving, therefore I should do something else, and therefore maybe I should explore other actions in order for this then hypothesized future to not to include an accident. And then you make the decision and eventually turn right or left or do something else or brake. You can watch the video. There are many other videos like this on YouTube. One thing which is kind of interesting is that most of the system I've showed you, at least when it involves having some kind of understanding of its environment, will involve usually cameras. So that means we have to have good algorithm to make sense of images. Okay, and so this is a whole field by itself, which we call computer vision. And in computer vision, a few key tasks are, for example, looking at the scene and then be able to locate all the objects. This is a task which we call object detection. So this is the task of, for example, delimiting a region in the image where we say there is an object around this rectangle and the object is of this class. This is a mug, this is a computer, this so on. Then we have also, as you see in the videos, human pose estimation, which is about putting like an artificial skeleton to know that this blob of pixels correspond to the head, these two blobs to arms, to the body, to legs, and so on. Then what you see now is known as segmentation, which is about classifying every pixel by a category, which is more or less like a finer version of object detection. Okay, so there is this one. You can also do, instead of just making rectangle and boxes or classifying pixels, you can translate images to text to have a description. This is what is shown in this video, but I will just skip it. I had also this example, but we didn't go over it, is can you have a system which is better than your, for example, dermatologist? And yes, when it comes to tasks which involve vision, we have very good system today, and some have been scientifically proven to be better than the best doctors, medical doctors. Then we finished with this question about paintings, composing music, writing funny stories. So I will just make you listen to this video. So what you will hear is an actual orchestra playing a partition which was written by an artificial intelligence program. So I'm not a musician, but if some of you are, I don't know if you could have said that this was, the partition was not written by a human composer. At least I would not be able to do so. Of course, you could always argue maybe this is just a very good copy of what humans have been composing as well, and I would not disagree with you. But then where is the boundary between a good copy and something really genuine and original? That's something maybe a bit more philosophical, but this is something we can do today, and you can appreciate whether or not this is worth listening. Okay, then yeah, there was this question. Most of these examples that I've been showing you are super exciting, but when it comes from, but they come from big companies which sit on huge data sets and have access to large amounts of compute. Is access to data and CPU powers mandatory to have AI breakthrough? So when it comes to neural networks and deep learning, I would say that yes, maybe unfortunately, to make anything reasonable, you need access to GPUs, but I don't think it's a that big of an obstacle for academic labs today. They've become quite cheap. Of course, you will not be able to compete with the kind of resources that Google, Facebook, Amazon, and others have, but you can build and have access to reasonable GPUs, and that's usually enough to make contributions in the field, or even develop your own applications. And this is something we are doing, for example, in our lab here at Montefiore, with our own GPU clusters, with today around 80 GPUs, and this is more than enough to fuel researchers from the department. So one example, for example, is this video that I will show you. And of course, not only it's about compute and data, it's also about having ideas. And to have good ideas, you only need a pencil and paper and then a laptop to implement it and evaluate whether or not it works. And there are still so many open questions, from deep mathematical questions to maybe other things that are more concrete when it comes to the implementation of all these things that do not require having access to this kind of resources. So if you want to work in that, yeah, don't worry. You don't need to work at Google to do AI, basically. Okay, and so this is a last example to conclude. And I waited to comment on your question because of this. So this is a master thesis, the outcome of a master thesis, which was carried out 2 years ago in the lab, together with at Montefiore and with the Department of Aerospace and Mechanics, where the student Normand, my student Normand, had to basically implement a small agent program that would control a robot to sort waste. And what we wanted to do was to speed up the sorting of this material. So what you have is, I'll just pause it. You have this thing in which you have, just for the purpose of the demonstration, you have pebbles, but you should imagine that in reality you would have like pieces of waste, and you want to sort them. For example, you want to put all the plastic together, you want to put all the metals of some kind in some bins and so on. And what we wanted to do was to control this robot, which is a gripper, which can grasp the object that are on the mill. And in order to accelerate the throughput, what we wanted to evaluate was whether the robot, instead of grasping the object, so this is like a cap, instead of grasping and then putting the robot, the cap or the pebble inside the bin, okay, this would take some time. What we wanted to evaluate was whether the robot could learn to throw directly from that position the pebble in the correct bin. So the purpose of this thesis was to learn this policy of throwing the object, of course, without failing. And so what you see is the robot learning. So it just evaluate. So this is at the beginning. Of course, it's very bad, and it cannot make sense of how it should throw these pebbles into the bin. But then after training, after learning, and again, what is interesting there is that we have never said to the robot how it should grasp the pebbles, what are the laws of motion that would govern the trajectory of the pebbles, because anyway we don't know the mass and other properties of the object we are grasping. But still it managed to learn a policy to just maximize the reward we wanted it to maximize, which was the probability of success when you throw the pebbles, so that it reaches the bin. So this is one example of the things we've done in the lab, but we have many other examples, but I would be happy to talk about it if we have the opportunity later. Okay, and then to conclude this first part for today's lecture, what you could already maybe perceive from these few videos is that many of them actually rely on pattern recognition. The fact that you have some input and then you recognize patterns, object in this input. But when it comes to AI, I think it's larger than that, more general than that, because AI is also about modeling the world. So that means explaining and understanding what we see. Okay, that's okay, you can do more or less with pattern recognition. But more importantly, it's about imagining things we could see but haven't yet. So it's about making sense of, let's say, several images that you would perceive in order to have a better understanding of the world. So maybe solve some ambiguity or gather some information in order to have a more accurate vision of the world. Or also to anticipate what would be the consequences of what you do in this world, or just anticipate how the world, the environment would evolve by itself. Okay. Then it's also it's also about problem solving and planning actions to make this thing real. So not only you have to simulate what would be the consequences of your actions, you have to decide what the actions you would take. So you would you have a large, usually a large array of different actions you could take. Which one do you take, and how do you find the best one? And how do you find it in a way which is efficient? Because again, you have a limited budget when it comes to computation. And it's also, of course, building new models as we learn more about the world. Okay, so that's it for this first part. So